I often tell non-geologists that I'm a climate detective. It certainly sounds sexier than paleoclimatologist. In paleoclimate science, we study and build models about Earth's past. Like a good forensic crime specialist, we use evidence-based research to answer important questions like how and why and when climate has changed. Our evidence comes from the scattered clues in the geologic record. But the geologic record can be a bit puzzling when it comes to atmospheric circulation. After all, we can't collect and analyze ancient air. My research works on this puzzle. Specifically, how did the atmospheric circulation respond to changes in global temperature over the past 30,000 years? I focus on the central equatorial Pacific, because there, the wind systems are dominated by the convergence of northern and southern hemisphere winds. The location of this boundary, also known as the thermal equator, in turn dictates the position of the tropical rain belts. But I still can't collect 30,000-year-old air, so I use dust. Winds can carry dust over incredibly large distances. For example, we find Saharan dust in Miami beaches. My dust records come from the middle of the Pacific. They were deposited by wind and then collected as marine sediment cores. I isolate the dust fraction from these sediments and then look for a sort of chemical fingerprint. Every particle of dust has a unique chemical composition, and I can compare the chemistry of my samples to the chemistry of deserts from across the world to determine their origin. I have found two main sources, Asia and South America, with the thermal equator in the middle. By comparing the changes in the source of dust through both time and space, I can see the shifts of the thermal equator. And I have determined that during the last ice age, the thermal equator was 3 degrees further south than it is today. But it can also migrate further north when global temperatures rise, as they did 6,000 years ago. Now, unlike a forensic crime specialist, a climate scientist not only has to reconstruct the past, but also to predict the future. My research shows that the atmosphere is incredibly sensitive to changes in global temperatures, and that the tropical rain belts can migrate. From there, we can move on to bigger questions, like how will this affect the tropical rain season or the intensity of typhoons? What areas will get drier and wetter as the thermal equator migrates? Nearly half of the world population lives on the equator, and we can only help them to adapt to climate change if we have accurate predictions. So we'll need some very good climate detectives. Thank you.